NASA has revealed an unexpected discovery on Mars. The space agency said it has spotted signs of large amounts of ice under the Martian equator, which was believed was dry. The discovery has baffled researchers, who have no idea how water ice would have been preserved there. Scientists were taking a new look at older data from NASA's longest operating Mars orbiter when they discovered evidence of significant hydration near the Martian equator. Jack Wilson, a postdoctoral researcher at the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland, led a team that reprocessed data collected from 2002 to 2009 by the neutron spectrometer instrument on NASA's Mars Odyssey spacecraft. In bringing the lower resolution compositional data into sharper focus, the scientists spotted unexpectedly high amounts of hydrogen, which at high latitudes is a sign of buried water ice around sections of the Martian equator. An accessible supply of water ice near the equator would be of interest in planning astronaut exploration of Mars. The amount of delivered mass needed for human exploration could be greatly reduced by using Martian natural resources for a water supply and as raw material for producing hydrogen fuel. By applying image reconstruction techniques often used to reduce blurring and remove noise from medical or spacecraft imaging data, Wilson's team improved the spatial resolution of the data from around 320 miles to 180 miles. It was as if we'd cut the spacecraft's orbital altitude in half, Wilson said, and it gave us a much better view of what's happening on the surface. The neutron spectrometer can't directly detect water, but by measuring neutrons, it can help scientists calculate the abundance of hydrogen and infer the presence of water or other hydrogen-bearing substances. Mars Odyssey's first major discovery in 2002 was abundant hydrogen just beneath the surface at high latitudes. In 2008, NASA's Phoenix Mars lander confirmed that the hydrogen was in the form of water ice. But at lower latitudes on Mars, water ice is not thought to be thermodynamically stable at any depth. The traces of excess hydrogen that Odyssey's original data showed at lower latitudes were initially explained as hydrated minerals, which other spacecraft and instruments have since observed. Wilson's team concentrated on those equatorial areas, particularly with a 600-mile stretch of loose, easily erodible material between the northern lowlands and southern highlands along the Medusae-Fossae Formation. Radar sounding scans of the area have suggested the presence of low-density volcanic deposits or water ice below the surface. But if the detected hydrogen were buried ice within the top meter of the surface, there would be more than would fit into pore space in soil, Wilson said. The radar data came from both the shallow radar on NASA's Mars Reconnaissance Orbiter and the Mars Advanced Radar for Subsurface and Ionospheric Sounding on the European Space Agency's Mars Express Orbiter, and would be consistent with no subsurface water ice near the equator. How water ice could be preserved there is a mystery. A leading theory suggests an ice and dust mixture from the polar areas could be cycled through the atmosphere when Mars' axial tilt was larger than it is today. But those conditions last occurred hundreds of thousands to millions of years ago. Water ice isn't expected to be stable at any depth in that area today, Wilson said, and any ice deposited there should be long gone. Additional protection might come from a cover of dust and a hardened crust that traps the humidity below the surface. But this is unlikely to prevent ice loss over time as scales of the axial tilt cycles. Perhaps the signature could be explained in terms of extensive deposits of hydrated salts, but how these hydrated salts came to be in the formation is also difficult to explain, Wilson added. So for now, the signature remains a mystery worthy of further study, and Mars continues to surprise us. Wilson led the research while at Durham University in the UK. His team, which includes members from NASA Ames Research Centre, the Planetary Science Institute and the Research Institute in Astrophysics and Planetology, published its findings this summer in the journal Icarus. It is the latest in a series of finds of signs of water on the red planet. In 2011, Lucindra Ojha accidentally discovered finger-style marks on Mars after studying images of the planet's surface taken by the Reconnaissance Orbiter in 2011. Not only did the markings appear to move, they did so in a pattern that would be consistent with flowing water. It was proposed these changes were caused by a volatile volatile substance, but the environment is too warm for carbon dioxide frost and too cold for pure water. Instead, it was suggested that a kind of brine was on or beneath the surface, and until now this had not been proved. Since its discovery, observations of similar sites on Mars have revealed that the finger-like patterns seem to emerge in warmer seasons and die away during cooler seasons. This was thought to signify the planet has flowing water and even an ocean under the surface that rises to during warmer weather. In his latest research, Mr. OJHA investigated the composition of these seasonal flows by studying their infrared wavelengths in each of the locations studied. The researchers found presence of hydrated salts during the times when the flows are most extensive, suggesting a link between the two. In particular, evidence was found for sodium perchlorate, magnesium perchlorate and magnesium chlorate, which are thought to be left behind when brine evaporates. The presence of perchlorate particularly suggests the water is briny rather than pure, and the researchers believe liquid water could be dissolving the perchlorates in the soil before reprecipitating them in higher concentrations. As the researchers don't know what the source of the water is, they don't currently know the precise processes in which the water is replenished. However, if the salts pull in moisture from the atmosphere as suggested in the paper, this could hydrate the soil, which helps develop perchlorates further and the cycle is repeated.